Hi everybody, welcome back to Physics Screencasts. Today what we're going to do is tackle some pretty complicated problems involving motion and motion graphing. Now if you've been with the program, you know that velocity has a couple of different definitions, speed has a couple of different definitions, and that you can use graphs of position versus time to understand those different kinds of motions. So just to talk through this problem in common sense terms, when I see a line headed down, and I see that it's a line, I realize that's a person moving at a steady speed in a negative direction. So they actually have a negative velocity, and that's because the line's headed downward. When I see this shape over here, what I think is that that's a person moving in the positive direction, basically, but the way that they're doing it isn't steady, because I see one kind of slope going on here, maybe it's like that, and I see a different kind of slope going on up here. So that to me looks like the slope increased, the speed increased. So this section of the graph, the second section, looks to me like the graph of someone who is speeding up. Now what question 6 is asking us to get into is the average velocity of object B between 5 and 15 seconds. So what we're going to do is zero in on this section of the graph between here and here. And the idea of average velocity is something that we use when a person hasn't been going a steady speed. Like this person has definitely not been going a steady speed. So I see that they started out kind of slow and ended up going pretty fast. But the way that I do average velocity is very similar to the way I do velocity. Average velocity is equal to displacement over time. And I know from practice that displacement is just how far I've gone. So it's position 2 minus position 1, and all I have to do is read off the graph where this person is and where they used to be. So what I see is the second position is 15 meters from the origin, and they started out the 5-second time period at 0 meters from the origin, so right on top of it. And time is going to ask us for the window of time over which the problem was happening. So that's 10 seconds, not 10 meters. And when all said and done, I'm going to end up with 1.5 meters per second for the average velocity that this person went over that 10-second window. The next thing that we're asked to figure out in question 7 is to talk about the concept of instantaneous velocity. Now, instantaneous velocity, you should know, is the speed of something, or the velocity of something rather, right now. So when they say at t equals 14, they don't care about the fact that this person was speeding up and was changing speeds all during the whole problem. What we're really going to zero in on is just right there, at t equals 14, how fast are they going? And what we're going to do is just kind of estimate this by eye. What I'm going to do is notice that the slope of the graph starts out pretty tamely, looks maybe like that, and by t equals 14, what I'm going to try to do is lay down a line that basically captures the slope. That's not the greatest line I've ever done. What I'm going to try to do is maybe I'll go blue and see if I can steepen it up a little bit. Maybe that looks a little bit more like the slope of the line. But anyway, what they're asking us for is not to actually figure this out. I could figure it out if I wanted to. What I could do would be, now that I've got a good triangle I feel happy about, a good line that captures the slope of the graph at t equals 14, I could get a rise over run going and actually figure out the slope of this line. What they really want to know is just, is this bigger than the average velocity? So what I'm going to do is just draw a line of average velocity, and that's going to be the line that connects the dots between where he started and where he ended up. And you can definitely see that the blue line's steeper than the red one, and so he's definitely going faster at t equals 14 seconds than he was on the average. And you can tell that because the slope of the line at t equals 14 is bigger than the slope of the line over the long haul. So for the final question on this set, what they're looking for is to figure out the average speed of B over the entire motion. And what we're going to do in this case is pull out a definition that we haven't used yet, and that is that speed is different than velocity because where velocity equals displacement over time, speed equals distance over time. And if you remember, the way that we count distance is that every step counts. So when I move from 15 meters down to 0 meters, the displacement would be minus 15, but the distance is the absolute value of that. So it's just straight up 15 meters. In the next section of the graph, this person moves from a position of 0 to a position of 15, and that distance is also 15 meters. And in the last section of the graph, it looks like they're not moving anywhere. So it looks to me like the total distance on this graph is 30 meters. And the total time that it takes over the whole graph is 20 seconds. So that's not so bad. When they say average speed, what they really mean is the overall distance divided by the overall time. And it's going to be 30 meters over 20 seconds. And that's something that works out to be 1.5 meters per second. So there you go. So in this set, question 9 follows right on the heels of question 8. We knew that from question 8, overall average speed is distance over time. And in question 9, average velocity is going to use a different definition. Overall average velocity is going to use displacement over time. And what we're going to do is go and figure out the displacements for each of these sections. But we already thought about that. The displacement of this first section right here is minus 15 meters. And the displacement overall for the next section was 15 meters. And the displacement for the last section was 0. So it looks to me like the overall displacement for the whole graph is 0. And that makes sense actually, because displacement is the kind of thing that accountants want to know about. If I end up in exactly the same place I started, my overall amount of change is nothing. And if the graph took 20 seconds or 30 seconds, it doesn't even matter. When the top of the fraction equals 0, I get that the average velocity of the whole thing is equal to 0. In question 10, what we're asking is the instantaneous velocity at t equals 3. And if you remember, when we looked at instantaneous velocity a minute ago, we had to look at the idea of taking a slope of the graph, but it was a little bit weird because the slope was hard to figure out. This one's not hard at all. If I go and take a look at t equals 3, I can zero in on a point right there. I know that this slope is a steady slope, so if I can just figure out the slope of this whole area, then I'll be able to know that the velocity was always the same all the time because the slope never changed. So when we get velocity, again, we're going to do velocity equals displacement over time. And in question 10, the person starts out at 15 meters and they end up at 0 meters. So it looks like our equation is going to be 0 meters minus 15 meters over 5 seconds. And wait a second, it looks like we get negative 3 meters per second is the average velocity for that first part of the graph. And actually that makes sense. The graph was headed downhill, so the velocity had to be minus because the person was going backwards in the negative direction. And that all should hold together. Okay, so almost there. One more and we're good. So to deal with the final question that we're being asked, we were told we're supposed to estimate the velocity of this person's movement at t equals 12 seconds. And so what I've done is I've blown up the graph here just a little bit to make it easier to look at. T equals 10, t equals 11, t equals 12 puts me right there. And I'm going to do my best attempt at drawing a straight line on the iPad. That's pretty good for me. And what I'm going to do now that I've got the slope of this swoopy line, but right here at t equals 12, what I'm going to do is try to pick just 2 points on the graph that are easy to read, and ideally they should be pretty far apart too. And I'm going to use those 2 points to get a rise or a run and to figure out a slope. So those look like 2 points that are pretty easy to deal with. This one right here looks like it's 20 seconds, 14 meters. And this point out here looks like it's 9 seconds, 0 meters. And it doesn't matter exactly what 2 points I pick, but these are on the line, so they're good, and I'm going to use them. So to get velocity, like I've been doing, I'm going to get displacement over time. And the velocity for this one is going to end up being 14 meters minus 0 over 20 seconds minus 9. And I get a velocity that's around 1 and 3 over 11, or I think I know this off the top of my head, about 1.27 meters per second. So that's an estimate, but that's good enough. So around 1 meter per second is the velocity of the person right at t equals 12. And there you go. That's a lot, but those are a lot of useful skills. So take care. See you soon. Bye-bye.